Hi guys, and welcome to my video on Venn diagrams and two-way tables, part of the Year 9 course. My name is Darren from Maths Guru. Thank you so very much for watching. If you can, do me a favor and subscribe to my YouTube channel. That one little click from you means a world to me. What do you mean it means a world to me? Who watches maths videos except you, me, and maybe my mother? But if you click that button, it lets me know that you're watching. Turn off notifications if you like. And head over to mathsguru.com. It says in the corner there, that will allow you to download notes, sign up for free, watch timecode videos, all of it is on there, and apparently it's quite useful. All right, so I normally start with the learning objectives, and by the end of this lesson, what do I want? I want you to understand and apply how to read and create a Venn diagram, know how to read and create a two-way table, know how to convert a Venn diagram into a two-way table and vice versa, and find probabilities of events from Venn diagrams and two-way tables. Seems like a lot, yes? Well, not really. Now, always recap our past learning, because I think that's incredibly important, because you need to know where you've been as well as where you are going. And this is all part of a probability series. So in the last lessons, we dealt with the very basics. And you're going to turn around and say, well, hold on a moment, that was really easy. Yes, it was. But in many cases, we're now going to use that probability stuff in terms of our Venn diagrams. Now, if you've never met a Venn diagram before, as I say here, maths meet art. What is a Venn diagram? Well, to be honest with you, it's pretty cool. And as I've said there, it was the reason I lost a mark in an exam in Year 9. Mrs. Hurst, I'm so sorry. It still hurts. It was the only year I was good at maths. Yeah, that's a bit worrying. I'm recording maths videos. But because I sucked at maths at school because I didn't understand it, hopefully these videos make a lot more sense. All right, so we can actually express the outcomes of certain events in a diagram called a Venn diagram. And I say here, we normally deal with two, and it's constructed in a very, very definite way. And here we go. Here are the important bits for a Venn diagram. Now, I always say to my students that little epsilon there, that little e there is so important. It should be at the top of every single Venn diagram, because what it means is that everything inside that square is a part of my probability or events. It encapsulates every single thing in there. And believe it or not, that epsilon there stands for my sample space. Now again, I'm getting a bit old in the tooth, and I can't quite remember whether we did that in the last lesson or it's coming up. But the sample space is basically all of the numbers or all of the events or the outcomes that are going to be from a particular experiment. So for example, if I had epsilon is equal with curly brackets 1, 2, 3, 4, 5, and 6, that would be the outcomes of a die, or the numbers that were possible from a die. Yeah, 1, 2, 3, 4, 5, and 6. So what I say here is we may have an event 1 is odd numbers on a die. So if I was going to say event 1, we would normally give that a letter. So let's call that A and B. And what I can do now is put an A on here and a B there. Now you're going to try and say, well, hold on a moment. Those two circles are very, very separate, aren't they? And I'm going to go, oh, yes, they are very separate. Why? Well, let's just see what happens. The odd numbers on the die, what are they? Well, they're the numbers 1, 3, and 5. And event B is going to be even numbers on a die, which would be 2, 4, and 6. And you'll notice in there, I'm writing inside those circles the numbers that correspond to each of those events. Now, is there any overlap between the numbers 1, 3, 5, 2, 4, and 6? And that is why the circles are very, very separate. There is absolutely no overlap. But there will be things that have an overlap. Now, as I say here, that there, when there is no overlap, they are called mutually exclusive. Yeah, there is no overlap. But what about if I had A, for example, as the numbers 1, 2, 3, and 4, he says doing some curly brackets, and B is the numbers 4, 5, and 6. Well, now what we can see is there is an overlap. We notice that the number 4 appears in both. And when the circles overlap, the reason there is a section is because I can write any of the numbers that overlap in that overlapping section. So I'd have the numbers 1, 2, 3 in just that section, with the 4 in both, and then the numbers 5 and 6 there. So copying in or filling in these Venn diagrams are freaking awesome. But it's really important to understand the sections of a Venn diagram. And as I say here, the section in the middle, all right, this little section here that I'm doing in red is where things overlap. And in many cases, I tend to write things down elsewhere so that I know where my overlap is before I put them in the Venn diagram. But before we get to those type of questions, let's look at this one here. We've been given an example where 12 people own a Mac and a PC. That sounds like a bit of an overlap here. So I'm going to say probably we're dealing with events A and B where we own a Mac, and let's say event B is we own a PC, or we have an overlap. Right, well, we now know that 12 people own a Mac and a PC. Where's that going to go? Well, I'm now going to write 12 in here. Now in that situation, it doesn't stand for a number 12 in the sense of the examples we did before. We now know there's 12 people in the overlap. I mean, I don't know their names. They could be Alice and Bob and Cheryl and Damien and Eliza, but that would be taking this a little bit far, and I don't think I know 12 people. But the point of it is, that's first tick. Thank you very much. It then goes on to say that 62 people own a PC. 62 people own a PC. Now that actually includes the people who own a PC and a Mac. Now for this situation, because I'm choosing event B for a PC, it means all of the people in the big circle I'm now drawing around really, really badly own a PC. Yeah? So, all right, so 62 people, I've already got 12 in the middle. How many people must be outside? Well, hopefully you will agree that 50 people there would be on that section there. Now, that's 50 people in just the section I'm going to shade for a moment, all right? Now, we wouldn't normally do the shading. I'm just trying to make it crystal clear for you guys so that we can see where it is. So now if I look at that whole circle of B, there's 50 and 12, 62 people own a PC. Ka-ching, what is it? 57 people own a Mac. That's 57 people in total own a Mac, but we already know that 12 people own a Mac and a PC. So if I do 57 minus 12, what do I get? I get 45, and lo and behold, 45. And again, this section that I'm going to backward shade here are the people who only own a Mac. All right, so there are 45 people who have a Mac, 12 people who have a Mac and a PC, and 50 people who just have a PC. See how these things begin to fill in? Now, in many cases, we actually can have another way of doing it. I like Venn diagrams because they're pretty funky, but what about a wonderful thing called a two-way table? A table, there is a table. Has it got two ways? It does, because it has rows and it has columns. Now, there is a trick to doing these things as well, and the trick is to notice here that A and not A. Now again, hopefully you realize that when we say not A, it's the opposite of A. So it's like the probability of it raining and it not raining. The probability of it being sunny and not sunny, for example. So in that situation, it is important to note that we have the A and the not A either in the same row or in the same column. In a previous school, sadly, I saw a member of staff teach this horribly, horribly wrong, who basically filled in the table with an A there and a B there and a not A there and a not B there. Now you're going to try and say, hold on a moment, what are those little lines? Also the same. There are so many ways in maths to try and trick you. It's nuts, isn't it? But again, we can use those little dashes, or we can say the word not, or believe it or not, we could even put a little line on the top, and that also means not. Yes, thank you, Barry. We really do not like you at this moment in time. So, being able to understand, A, how to set up a two-way table is really, really important. But how do we actually fill it in? Well, let's go back to our previous example. Now, I'm going to write the word and here, which really upset my students because they were like, I'm just going to use that as some sort of theoretical, and it's sort of my mind, but and in maths has a very specific meaning, right? So I'm going to turn around now and say, let's say that A is equal to, what did I have it as before? Let's see if we can keep it the same, Mac. So A is Mac and B is PC. So again, let's go back. We've got 12 people who had both. All right, so 12 people who had both. That's 12 people who had an A and a B, because A is a Mac, B is a PC, and that goes here. So this box, I always remember, is the intersection of that Venn diagram. Really, really important. Okay, now it says 62 people own a PC. So 62 people own a PC. Now again, another box that tricks people is that total box at the end. So if I'm owning a PC, all right, and PC is B, that means that the total people who own a PC are actually going to go in there. So the 62 people own a PC, so there's 62 people own a PC. And does that mean we can now find a missing value? Absolutely. I can find this not PC, right? Because in that situation, the 12 and the 62 must, sorry, the 12 and this other number must add to give 62. So that would have to be 50 do not own a PC. So let's just check. Did 50 people not own a PC? Absolutely, because in that situation, 50 people had a Mac. Whoa! All right, so what about the next one? It says 52 people own a Mac. Well, A is a Mac, we want totals. We're giving a total. So now I know 52 people goes in there. Sorry, I misread that. Try that one again. Oh, he says rubbing it out. So it said 57 people own a Mac. Read that properly. So 57 own a Mac. So I'm going to put 57 in there. Well, the columns must add together. So a 12 and whatever must add up to 57. Well, what is that going to be? So that's going to be 45. Ka-ching. Thank you very much. Right, how many people? Oh, interestingly, what is this box here that I'm putting a square around there? What does that mean? Well, that will be the people who don't own a Mac and don't own a PC. Well, it didn't say anything in there about that. So actually, I'm going to write that as 0 because it doesn't give me information about anyone who doesn't own a Mac or a PC. Right, so the columns add together. So 50 plus 0 gives me 50. The rows must add. 45 plus 0 gives me 45. Now, what I'm going to do is use a pretty interesting technique called double accounting, where what we do is we add the numbers in the rows and we add the numbers in the columns and check that they match. So if I do 62 and 45, it gives me 107. So 62 and 45 is that. If I add 50 and 57, I get 107. And so, ka-ching, I know I've done it right because all of the numbers add up and they meet in that bottom corner. So again, reading this information is really, really important. So let's have a look at some examples. Find the probabilities, find the following probabilities. So again, we got a piece of information here. Now we got a new number. What on earth does that number outside the circle mean? Well, I mentioned it a moment ago, actually. It means that there are 7 people who do not own a computer at all. Oh, so let's see. Let's see what this 31 means. 31 means owns just a Mac. 50 owns just a PC. 12 people own both. All right, now listen to the word I said a moment ago, just a PC. Because if I actually want to know how many people have a PC, that's everyone in that PC circle. So let's see now. Again, we've got to be very careful here because it says PR. So now because it's PR, I want a fraction. So the probability of people who own a Mac. So first things first, I want the total number of people who own a Mac. Well, that will be 31 plus 12, which will give me 43. Out of how many people were there altogether? Well, that's where we have to add all of the numbers in the Venn diagram. Because remember, there are 31 people who own just a Mac, 12 people who own both, 50 people who own a PC, and 7 people who own neither. So if we add those up together, that's going to give me that 5, 6, 7, 8, 9, and oh, he says not being able to add 100. Well, that's a bit of a fluke, don't you think? So we get 43 out of 100 gives me the probability of Mac. Now, can I cancel that down? Nope, because 43 is a prime number. So that's probability of Mac. What about the probability of only a Mac? Now, again, in that situation, I used the word just a moment ago, but only works as well. How many people are only owning a Mac? They can't own a Mac and a PC, it's just a Mac. And there we go, if we read that off, that gives me 31 on 100. What about the probability they own a Mac or a PC? Now, again, a lot of people get tricked there because they think that's the overlap. The overlap is and. This is really saying how many people own a computer. Now, again, there's lots of ways of doing this. I tend to look at this little number down in this corner here and say, well, if there's 7 people who don't own a computer, there must be 93 people who did own a computer. So I'm going to write 93 down here, 93 out of 100. But is there another way I could have found this? Well, yes, because what I'm trying to do is add together then all the numbers in those 2 circles. Because 31 own a Mac, 12 own a Mac and a PC, 50 own a PC, so all of those people own a computer, and that's going to be 93. So the probability now of a Mac and a PC, and again, knowing this is the middle section, that's going to give me 12 on 100. And would I leave my answer like that? Nope. Why? Because you have to cancel it down. Yes. So I'm going to cancel it down to 6 on 50. Am I done? Nope. That's going to give me 3 on 25. And does 3 go into 25? Not when I was at school. And there we go. We've done some probabilities from a Venn diagram. What about a two-way table? Can we do the same thing? I should, Coco. Now again, I'm fairly sure this is the same information, but let's just see if we can read it out. So again, I want the probability of a Mac. How many people in total own a Mac? Now again, did you hear what I said there? In total. And wherever you're looking for a total, it is the number at the very bottom of that one. So we know that this here is our Mac column. The total number of people who own a Mac would be 43. So again, I could read that information there as 43 over 100. The probability of someone owning only a Mac, that means they own a Mac, but they don't own a PC. Okay, so where is Mac, but no PC? Well, again, we're in the Mac column, but we want no PC. So there we go. So a Mac, but with no PC. So that would be 31 on 100. Let's just check. 31 over 100, 31 over 100. Same information, just done in a different way. The probability of a Mac or a PC. Now in this situation, again, I probably would have looked at the people who didn't own a Mac or a PC and taken it away from my total there, which is 100. So that would have given me my 93 on 100. Another way to remember it is when you are doing an OR, you are basically going to add together the boxes I'm about to shade in. So when you're doing an OR, you can have all of those three numbers added together. All right, now I know that's going to make it harder to see, but hopefully if you're watching this, you can make your own notes. And have I mentioned these notes are downloadable from mathsguru.com? Of course they're downloadable from mathsguru.com. What about the probability a Mac and a PC? So where do they overlap? Where is there a Mac and a PC? Absolutely, it's going to be this one here with 12. So that's going to be 12 on 100, which is 6 on 50. And again, I don't try and do anything else other than keep halving and halving and halving until I get to maybe 3s. 6 is going to give me 3 on 25. And I know that 3 doesn't go into my 25 times table. And there we go. So again, as I've said, the total columns here are really, really important because in an exam question, I've known them actually give the totals. So they may give you a value here. They may give you the total here. They may give you a total here. Yeah, they may give you a total here. And they may give you a total there. Now, generally speaking, if they give you 4 pieces of information, you can find absolutely everything else on that table just by doing the basic taking away. Because if you know that all the values add together. So, for example, I can find this one here by using numbers 1 and 2. I can then find this number here by using the dot and the 3, and so it goes on, right? I won't try and make this any more complicated than it already is. Let's do a couple of examples. A survey of 30 people found that 21 like AFL, 12 like soccer, and 7 people like AFL and soccer, 4 like neither. All right, okay then, so I'm going to do A and S. You don't have to call them A and B, you can call them whatever you like, but I normally use letters that make sense to me. Alrighty-o. 4 like neither of them. Well, I'm going to put 4 out there because they don't like anything, pretty much like me. 7 like both, 7 in the middle. 30 people found that 21 like AFL. That's 21 people like AFL, not just AFL, they're like AFL. So we've already got 7 in the middle, 21 in total. I'm imagining that's going to give me 14 there. What does it say? 12 like soccer. So I've got 7 in that middle. So what have I got? 7, 8, 9, 10, 11, 12. Using my fingers, yes. That gives me 5 there. So now having got the number of people, we can actually answer this all together. How many people like AFL or soccer? Now they want a number of people. I'm going to introduce a new little letter here. That's called N. So I'm going to put A or S, all right? N stands for the number of people. Yeah, it's very, very different. And N is awesome in maths. How many people like AFL or soccer? Now, how do we do that? When it's an OR, you add all the numbers in the circles. So 14, 21, 26. So I'm going to write there just 26. It's not a probability. Don't divide it by anything. It's just 26. Okay, so now moving on to how many people do not like AFL. Sorry, how many people do not like soccer? All right, so I'm going to write the number of people who don't like soccer. Oh, pen change. Now, do not like soccer. How are we going to do this one? Well, there are 7 people who like both. 5 people who really just like soccer. So that's 12 people. How many people in total were there? Well, we can add 14, 7, and 5, which gave me the 26 plus the 4, 30. So 30 people in total. And I'm going to take away the 12 people who like soccer. And there we go. That's going to give me 18. Now, that's going to give me 18 people who don't like soccer. And you've got to remember that these 4 people here don't like soccer and they don't like AFL. So they're included in that. Really, really important to know they're included in that. All right, how many people like only AFL? So a number of people who only like AFL. Let's see, how many people only like AFL? Well, in that situation, it's the section in just this bit here. And so that is going to be 14, right? Because they can't like AFL and soccer. It can't be that middle bit. Has to just be the 14. Right, if one of the 30 players was randomly selected, now I know I feel like I've got probability coming up. Find the probability they like AFL and soccer. So AFL and soccer, well, that's that overlap. So that's going to be 7 on 30 because there's 7 people who like both out of the 30 people. The probability they like neither AFL, so AFL and soccer, they don't like AFL and they don't like soccer. How many people? Oh, 4, because it's 4 out of 30. Do I leave my answer like that? Nope, because they're both even numbers. So that becomes 2 on 15. And again, if you don't cancel down in maths, sadly, you're going to lose the marks. And the probability that they only like soccer, well, how many people only like soccer? And in that situation, there are 5 people, all right? So they can't like both, just the people who like soccer. So it's 5 people out of 30. They both divide by 5, which gives me 1 out of 6. Now let's move on to an example about using a two-way table. At a car yard, 24 cars are tested for fuel used. There's 24 cars in total. So the first thing I'm going to do is going to write 24 in there. They give me 1 piece of information. Remember, they probably normally give me 4. Right, what do we got? So 18 of the cars run on petrol. That's a total. The total number of cars who run on petrol is 18. There we go. So that's 18. 8 cars run on gas. Right, so the total number of cars is 8. And 3 can run on both. There we go. So they give me 3. And what did I tell you? Oh yes, they've only got to give you 4 pieces of information and we can get the rest. So looking at that row first, I've got 3 plus something must give me 8. That would have to be 5. Now I'm going to look at the column with the 3 in. 3 plus something must give me the 18. That must be 15. Let's look at the bottom row. 18 plus something is 24. Well, that's got to be 6. 5 plus something gives me 6. That's got to be 1. 15 plus 1 gives me 16. And then I'm just going to check, does my 8 plus 16 give me 24? It does. Does 18 plus 6 give me 24? It does. And so my table works. Okay? I've either been extraordinarily lucky and fluked it, or that's the right answer. So here we go. Illustrate the situation using the two-way table, and then how many of the cars do not run on gas? So the number who do not run on gas. So not gas is this one here. Total number of cars would be in that situation 16. I'm just going to read that number off of the total. Run on neither petrol or gas. So the number of neither petrol or gas. I'm going to write nor gas in there. Not petrol, not gas. Well, that's going to be, this is a number here. So the ones that are not petrol and not gas is going to be 1. Well, it's just 1. So just write 1 because I want the number of. All right, so find the probability that a randomly selected car runs on gas. So now we want the probability of running on gas. Well, how many people run on gas? How many cars run on gas? 8. So that's going to be 8 out of 24. Well, both those numbers divide by 8. That's going to give me a probability of 1/3. Runs on only gas. The probability on only gas. Ooh, so that's gas, but not petrol. All right, so gas, but not petrol. All right, so there is going to be 5 of those because you're looking at the gas, but not petrol, where they interact would be 5 on 24. No numbers going to 5 and 24, leaving that one there. The probability of gas or petrol. Now, when I want gas or petrol, I'm going to add up that number, and that number there, right? They are the gas or petrol numbers. Alternatively, I could have taken this little number here with an X, taken it away from 24, which gave me 23 on 24. And there we go. That's the end of this video. Thank you very much for watching. Hopefully you found it useful. There's a lot more to come, but I'm going to call it a day for this one. So please take care and stay safe. Bye-bye.